And so today what we're going to talk about are polynomial functions. We're going to look at them in a little deeper sense than we looked at last week. So a couple things that I did say about polynomial functions is that their long-term behavior follows power functions of the same degree. So if you have an x squared, it's going as your leading term, it's going to follow the long-term behavior of a f at x equals x squared, and so on. Now, its short-term behavior is going to be kind of dictated by the roots of the equation. And so the roots of the equation, of course, are the x-intercepts, and then you're going to have one more point that always happens so long as you have a domain that includes x equals 0, is that you have a y-intercept as well. And so to get the y-intercept is fairly straightforward. You just figure where does f at 0, what does that equal? And it's usually just the constant term. Not usually, it always is just the constant term. And so that's easy to look at. You ignore all the terms that involve an x, and you just look at the constant term by itself, and you get that. The x-intercepts you get by a number of ways, and the way that we're going to look at it mostly, since we're going to deal mostly with just integer roots and things like that, is that we're going to look at these by factoring. Now, factoring is a pretty large subject, and it's a pretty intense thing when your polynomials are of a higher degree. Then there's a lot of work to do. But in general, what we're going to do is just either have the polynomials already factored, and that's probably going to be the predominant case, and then occasionally I might have you factor a polynomial. Now, you all should be pretty familiar with how you factor a quadratic equation, something like 3x squared plus 6x minus 1. You know how to approach those kinds of things. But when you have a higher degree, there's some clues as to how you can get this thing factored. So if you look at the first and the last terms, so the leading coefficient and the constant term at the end, the ratio of those two, all the positives and minuses and all the factors of them, will tell you what the candidates are. So in this case, the candidates that you would look at would be anything that's a factor of -6 over anything that's a factor of 1. And so your candidates would be plus or minus 1, 2, 3, and 6. And so you don't have to try everything in the book. You just try those kinds of ratios. Now, you may end up with some polynomials that you have a lot of candidates to try, but at least you have a finite set to try. So let me give an example of one. And I don't know if you remember how to do synthetic division or not, but synthetic division is really helpful here because it makes your factoring go much, much faster. So let's say we have this polynomial.
What was the potential factors?
It's the ratio of the constant term divided by the leading term.
So just 6.
So this would be -6 and divided by 1, or all the factors of that. So it would be -1, -6, -3, -2. Okay, so in this one, what you want to try is start doing some of those candidates. And so I just, as a matter of habit, just always use the small numbers first because they tend to be easier to work with. So if you remember how synthetic division goes, you basically set up the coefficients in order like this, and then you take the negative of the root that you're trying. So here I'm actually trying the -1, x minus 1 would be the thing that I'm trying here. And so the way this works is that I would bring down the 1, and then 1 times 1 is 1, and then add 2 plus 1, and you get the 3. And then you get the 1 times 3 equals 3, and so -5 plus 3 is -2. And then you take -2 times 1, and you get -2, and you add -6 and -2, and you get a -8. So the fact that you have that -8, that's the remainder of this division. And what we're looking for are factors, and we don't want any remainders, so we can discard this as a candidate. So the next one to try would be -1. So I do the same thing with -1. And so I bring down the 1, and I have -1 times 1. And so 2 minus 1 is 1. And then I have -1 times 1 is -1, and you have the -5 minus 1 is -6. And now I get a +6, and -6 and 6 is 0. So I have my first factor here. And from this point, since I have just a t cubed, that last line, the 1, 1, -6, means that I have, after I've divided by -1, I have this t squared plus t minus 6. And at this point, this is an easy thing to factor. And of course, that factors into t plus 3 times t minus 2. And so our whole function then is going to be t plus 1, t plus 3, t minus 2. So you notice how when I'm trying that -1, I use the opposite sign in my factor to be t plus 1. So this is the complete factorization of that polynomial at the top. Now there's a number of ways to do this. And like I said, we're not going to do a lot of this kind of stuff, but I think most of you have learned synthetic division, and it's probably a good time to review it because it is handy, and particularly as we go through dealing with more and more polynomials, factoring is going to become kind of a fact of life. So I always find that using synthetic division is the one of the most efficient ways to determine if you have factors or not. So if we were to graph this, my three roots are -3, -1, and +2. So I'm going to expect my curve to go through those points. Now the other point that I have is, remember I have the y-intercept, and if I just put t equals 0 in the top polynomial, you see that f at 0 is just going to be -6 because all the terms that are involved with x, or t in this case, go to 0. And so I can mark my -6. Now remember, the long-term behavior of this thing follows just the function f at x equals x cubed. So you know that with a third power, you're going to start from the lower left and go to the upper right, right? That's the long-term behavior. So if we start there, we can make a pretty good guess as to what this polynomial looks like when you graph it. Now the one thing we don't know about this, now that should have gone exactly through -6 on there. It looks like I was a little short. But what we don't really know is how high is that peak in between -3 and -1. And so you can estimate this just by plugging in -2. You don't know that the peak actually happens at -2. We're going to figure out how to determine where that peak is and then what the value is. But for now, we just have this general shape. And so those 4 points give us a pretty good idea of what this graph is going to look like. All right, so let's look at another one here. I'm going to have t to the 4th minus 4 times t squared. Okay, so this one factors fairly easily, right? You can first factor out a t squared on here, and then we have t squared minus 4 remaining. And so then t squared minus 4 in turn factors to t minus 2 times t plus 2. So this is a fully factored form, right? So what's the long-term behavior? It's going to look like a t to the 4th function, right? Where we don't have a negative in front of that t to the 4th, so it's going to come from the upper left and it's going to go to the upper right. And so then we're going to look at our roots, and the roots of this thing, or the x-intercepts, it's going to be at 0, -2, and 2. So we have these 3 points. Now think about it for a minute. What's the shape of this graph? What's the possible, our y-intercept corresponds to one of the roots, right? Where you have x or t equals 0, and then f at 0 equals 0. So that one's already there. That's not going to help us. So what does this look like? So if we're just going to kind of go through the points, we're going to end up where we can't really get right back up to where we started without doing something a little trickier. Okay, so I put this in a little graphing program, and I get this thing that looks like this. It almost looks like a cross section of a molar, right, with two little cusps on there. So we scratch our head and you wonder, okay, what's really going on here? You can see the roots of the -2 and the 2. You know, it goes straight through, but where you have the root where you have 0, 0, it just kind of touches the axis and then it turns around. And in fact, that should remind you a little bit of what a parabola does, right? When you have f at x equals x squared, it goes down to the origin and then turns right back around. It doesn't really go through. It just merely touches it. So if you look at the original function in terms of its factored form, you have a t squared there. So it turns out that when you have these roots, these are called multiple roots, that they have a different behavior than just going through the line. And so we have, we're going to be looking at 3 different cases. And so we have this repeated roots thing here, where let's say I have this function that has both a first, or it has a first, second, and third degree terms in there. So the roots here are easy enough to determine. It's -3, -2, and 1. But you have these powers in here, and the question is, what happens with the power then? Okay, so when you have just a single root like that, x plus 3, there's no exponent to that. So the first degree, it always passes through. And when you think about it, what happens when you go from one side of the equation to the other, or one side of this root to the other, you're either going to go from positive to negative or negative to positive, right? That's what happens with x plus 3. So when you're less than -3, let's say -4, you're going to have a negative number. And when you're on the other side of it, you're going to have a positive number, so -2. So my little mark there going through is perhaps wrong. It may go the other way, but it's going to go straight through. It's going to go from negative to positive or positive to negative. Now with the squared, we've seen this one already, where you have something like this, where you have -2 is the root to that second term, and there we have it squared. And remember what happened in the last slide, where it just touches the axis and turns around. And that's the case always when you have a term that has a square in it. And when you think about what happens to the sign, if this function is positive, as you go through this one point, it's going to go from positive to positive, right? Because it's not going to change sign with this with the squared. It's always going to stay positive. But if the rest of the function is negative, it's going to go from negative and not change signs while we go beyond -2. And I'll set up a little table in a little bit to show you how this works on a couple other polynomials as well. Now the third degree, what happens, if you remember when we had the power functions, the higher the degree that we had, the more it would flatten out. Remember how a parabola was a pretty nice point, and then as we get to x to the 4th, it starts getting wider and wider where it seems like it touches. And this is the same thing that happens with third degree. It behaves like a first degree. It goes from a negative to a positive, or from a positive to a negative, but it's going to kind of linger there a little bit. So it's going to flatten. And so this is a real telltale that you have this sort of thing going on, where it's not just the exponent's not just 1, it's more like 3. And so if I put this in my program again and I plot it, you can see what happens here. It goes straight through the -3. It comes up and it touches the -2, and then it goes through the axes here, and then at 1 it kind of flattens out and goes up. Now let's think about what we would know about this one in terms of long-term behavior. We have an x squared, and an x cubed. And when we multiply all those together, we get an x to the 6th. And so an even power with a positive coefficient comes from the upper left, and it goes to the upper right. So this graph agrees with what we expect here. Okay, so we'll take a couple examples of this, but for now, are there any questions before we go on? Yes?
So does it do the same, like if it's 4th degree, does it still just touch, and if it's like 7th degree, it still flattens and then goes through?
That's correct. And so when you have additional even degrees, instead of just touching, you know, what would remind you a little bit of a parabola, it starts to flatten out as well. It starts to broaden out.
And that part where it dips down again into the negative, how can you predict that behavior when you're drawing?
We're going to get to that.
Okay.
That's a good question. Okay, so why don't you try this one? Okay, take a look at this. Look at all the things that you know about this. Look at what you would expect is the long-term behavior. Look at the roots and contemplate what the roots will do in terms of their behavior around the axes. And I'll give you a couple minutes to look at this. So what does this thing do? So the thing that you want to do is make a list of the things that you know about it. The y-intercept is going to be just where you have f at 0. So all the x's drop away, and so you have negative 2 times 3 squared minus 1, and you get 18. So you know that wherever you're going to go with this thing, x equals 0 means that f at 0 is going to be at 18. Now your x-intercepts, you have negative 3 and you have 1. And so the negative 3, because that's squared, we're going to look at that as a double. So that means wherever it's going to come from, it's going to just touch the axis and turn around. And so the long-term behavior, it's 3rd degree, so you would normally expect it to come from the lower left and go to the upper right. But it has a negative coefficient, so it's going to come from the upper left and go to the lower right. So you're going to expect, when your numbers are really large, that they're going to be off to the sides like that.
Wait, why is it 3rd degree?
It's 3rd degree. Think about when you expand this polynomial, you're going to have one term. The leading term is going to be just all the first terms to whatever power they're going to be. So x plus 3 squared expands to something x squared, and then some lesser degree terms, and then, of course, x. So you have x squared times x when you multiply it out.
So when you multiply everything out, it's 3rd degree.
Yeah, so just imagine the leading term on all these things getting multiplied out, and so you can safely take that x and apply whatever exponent you have, and then the cumulative exponent is what your ultimate degree is. Yes?
Just to double check. So originally it would have gone from, the arrows would have switched, and it would have
Gone from the lower
to the
lower
upper
left
right,
to the upper right.
but because the coefficient
You have a
is
negative
so you switch
coefficient,
it.
right. So just imagine if at some point you have x equals minus 10, you know, with a normal 3rd degree it's going to be negative whatever, something like to the 1,000, right? Because negative 10 to the 10 cubed is going to be negative 1,000.
And you just,
And so it's going to be the negative of that, so it's positive.
okay.
Okay, so we can make a sketch now. We put our points down. We know we have an 18, and we know we have the negative 3 and 1. And so it's going to come from the upper right, just touch at 3, turn right around. Now what I don't know here, and what the graph may or may not be accurate in, is there a peak somewhere around negative 1 or negative 2 that's way off the chart? You know, that's something way higher than 18. It's quite well possible. It might even kind of come up a little bit slower, and that peak may happen on the right side of 18. And the question about where the local minimum and local maximums are, we're going to use our knowledge of derivatives to calculate that, probably next week. Okay, so that's graphing. Now what I want to do here is I want to start making equations. Let's say I know where my zeros are. I know what certain values are. Can I form a function that that includes all those points. Okay, it's one thing to take a function and to graph it, right? You can tell a machine to do that. But what about the other way around? What happens if you know where the roots are, but you don't necessarily know what the function is? So what we're going to do is we're going to make up this function by using the x-intercepts as our factors. And then we're going to use a coefficient in front of those factors to get us where we need to be to include that one point that is not an x-intercept. So when you think about it, if you have a cubic equation, a third-degree equation, that means you have potentially 3 roots, and then you need one more. So you need 4 points to determine a cubic equation. A polynomial that has a 4th degree, you need 5. Okay, and so you always need one more than your degree to establish that equation. Okay, so let's look at this. If we have a function, and we know the roots are going to be -2 and 1 and 3, and we also have a y-intercept of 2. Okay, so here's the procedure. What we want to do is we want to set up our function where we're going to have this coefficient a times all the factors that involve the roots. And so if I plug in the numbers here, I don't know what a is yet, but I do know what my roots are, so I'm going to put x plus 2, x minus 1, x minus 3. Notice I got the signs right? With a -2 as the x as the root. When x equals -2, then that factor has to be x plus 2 to make that 0. Now I want to make a comment here. I'm asking to find a function. Now it's possible that you have many functions and functions that may look entirely different that will satisfy these criteria. So what we're really looking for is an example of the function, not necessarily a unique solution to this, because there can be more solutions than just this one. Okay, so how do we find a then? So what we do is we say, all right, we have this remaining point, and we're going to stick that in the equation. And so we know f at 0 equals 2. And so I'm going to plug in a 0 wherever my x is, and then simplify from there. So I get 2 equals a times 2 times -1 times -3. And when I do all my math, I get a equals 1/3. So now I have all the pieces. I have all my terms that involve x, and I have that coefficient. Yes?
So even with the y-intercept, there's more than one function possible?
It's possible. Okay? Now, it's a much different kind of question to say, what is the general solution? In other words, the solution that encompasses all possible solutions, and we're not going to go there. We're going to construct one solution based on what we know about the behavior of polynomials. Okay? And there's not going to be any variables in this when we lay it out, because here we have the solution. F at x equals 1/3 times x plus 2, x minus 1, and x minus 3. So you plug in your points, and you can see that all of these things work. Okay, so if we say -2, well, that first term is 0. If we say 1, then the second term is 0. And if we say 3, that third term is 0. So our roots are satisfied by this equation. And then so if we stick in a 0, we have 1/3 times 2 times -1 times -3. That will become 6/3, which is 2, and that's our third, or excuse me, our fourth point. F at 0 equals 2. Okay, time for you to try one. So I want you to find a function that have these points. 1, -4, and 0, -8. All right, so let's see what we got here. All right, so the general form of the function, and I'll just put the roots right in, is going to be f at x equals a times x minus 1 and x plus 4. And so we know that f at 0 is negative 8, so then we're going to write the rest of that equation with x equals 0 in it, and then we'll simplify that, and we get negative 8 equals negative 4a, and a then equals 2, and our full function then is f at x equals 2 times x minus 1 times x plus 4. All right, any questions? Okay, so that was the bare bones. If we know what the intercepts are, and or the we know what the roots are. Now, what I did was I assumed that all of those roots were just single roots, that we didn't have any multiple roots or so. Now, we could specify that 1 or the negative 4 was a double root, then it would look entirely different if we were to plot it, and we would get an entirely different function. So there are ways that we can, with the same data, get many different kinds of solutions. But let's say we have this graph now, and I know you probably can't read the numbers, so I put put all the values of the 4 values here of the intercepts. So we have an intercept that starts from the left, and you can see that's a negative 1 and 0. And then we have at 0, x equals 0, then y equals negative 4. And we have an intercept at 1 and then another one at 2. So let's look through those and think about what we know about the shape of this function based on having multiple roots. And so if I start the same way, if I say, okay, I still have that factor a because that's going to give me the scale sufficient to give me that negative 4 where x equals 0, I'm going to put my roots out just like I did before, but we know we have multiple roots now, right, by the shape of this thing. So we know at x equals negative 1 that we have a triple root, and at x equals 1 we have a double root, and x equals 2 we have just a single root. So we're going to have those exponents in there. And that's based on that rule that I had earlier, that it goes straight through with an exponent of 1. It just touches and returns in the same direction if you have an exponent of 2, and it kind of flattens out and then crosses the axis where you have a cube. Yes?
What is the number for the y-intercept in this?
It's 0, negative 4.
Okay, so the point is.
Yes. Okay, so now that we have this part here, we can figure out what a is by doing the same thing that we did on those other ones, where you just stick in our point and see what a has to be to make that point work. And so f at 0 is going to be 1 cubed times negative 1 squared times negative 2 equals 4. That's where we get f at 0 equals negative 4. And so then I multiply out those factors in parentheses, and I get negative 2a equals negative 4, and so a equals 2. And so my function then turns out to be 2 times x plus 1 cubed times x minus 1 squared times x minus 2. Okay. So I'd like you to try this one. Here's my points. The x-intercepts are negative 2, negative 1, and 1. And the y-intercept at 0 is going to be 1. Okay, so let's see what we got here. So we know that we have, because of the roots, we have these factors, x plus 2, x plus 1, and x minus 1. And then we look at the first one, and that goes straight through, so that's just an exponent of 1. The second one turns around, and so that's going to be an exponent of 2. And the third one turns around, and that one's going to be an exponent of 2 as well. So we're going to expect those two factors to be a squared. So then to figure out what a is, we know f at 0 equals 1, and so we'll plug in all the numbers where x is 0, and so we get 1 equals a times 2, and what we get is a equals 1/2, and our function then is going to be 1/2 x plus 2 times x plus 1 squared times x minus 1 squared. Okay, so we're going to shift gears a little bit here and talk about solving inequalities of polynomials. So here's a polynomial expression that looks kind of like the functions that we were looking at, except that I'm going to say this thing has to be greater than 0. So this thing has a solution set now, right? Just like when you have any inequality, there's not going to be just a single value of x. You're going to have a set of values of x. Now we also know that if this thing was an equality, that we would have solutions at, if this was a function at the roots, right, where x equals -2, -1, and 1. Now the inequality is going to change from a positive to a negative number. And when you think about where can that occur, think about what happens when you have a root. Like it goes through the axis, so the function value goes from a negative to a positive, or from a positive to a negative. So it would make sense then that your only possible places where this function can go from true to false, if you want to look at it that way, from where that expression is greater than 0, or the false case is where it's not greater than 0, it's going to happen at those points. And so what we need to do is take a look at the intervals that are bounded by those points. And so I'll make a list of those. So since there's going to be three possible places where it changes, we actually have 4 roots, or 4 intervals that we look at. So we look at from -∞ to -2, and then from -2 to -1. Because at -2 you could potentially change from a negative to a positive, the value of that expression. And so we set up this kind of table where we have these intervals, and then we're going to look at our factors and see how the factors behave. And then we're going to ask ourselves, with those factors given the way they are they going to be greater than 0, or is it going to be less than 0? And so let's look at the first column. In between -∞ to -2, x plus 2 is negative, right? Because if x equals -2, it's going to be 0. But we're not interested in we know it's a root, so it's going to be 0. But let's say it's -3 or -4 or -5 or anything to -∞. That particular term is going to be negative. Now, if we go from -2 to -1, we know it's going to be positive, right? Because if something in between it, like -1.5 plus 2, is going to be positive 1/2. So you can pick a number that's midway in between, and you know that whole interval is going to always either be positive or negative. It can't change because it would have to go through the x-axis and establish another root. So in this case, we look at those 4 intervals, and the only case where x plus 2 is negative is where x is less than -2. Now, this next case, if we look at it with the exponent, so we have x plus 1 squared, that's always going to be positive, right? No matter what the value of x is, since you're squaring it, it's always going to be positive. So we can just write our positives all the way down. Now at this negative, or at x minus 1, in the first interval from -∞ to -2, that's always going to be negative. In the second one, it's always going to be negative, right? Because you have -2 minus 1 is -3, all the way to -1 minus 1 is -2. The third one still is going to be negative, because if you look at 0, which is in the middle of that interval, 0 minus 1 is negative. Only the last one of those intervals is going to be positive. So when we make our list of pluses and minuses, the only one that is positive is going to be the bottom. Now when these three factors multiply, it'll tell us what the sign is of the whole expression, right? If we have a negative times a positive times a negative, we get a positive number. So that's greater than 0. So we can mark a plus there. The next one, we have a positive number times a positive number times a negative number, and that's always a negative number then. Same thing with the third interval. Positive, positive, negative makes a negative. And then the case where all the factors are positive, we're going to have, it's going to be true because the expression is going to be greater than 0. So the solution set then, we write it in terms of interval notation. And from negative infinity to negative 2, that's true. And from 2 to infinity, it's true. So we write down the intervals where it's true. You had a question.
Sorry, how does the first set of like negative infinity to negative 2, how does that end up multiplying out to be positive?
Because we have a negative number times a positive number, so you'll still have a negative number, and then times a negative number becomes positive. If you multiply an even number of negative numbers together, they'll make a positive number. So negative 1 times negative 2 is positive 2.
Because that one's squared.
That's the first one. Oh, then the squared is always positive because any number squared is positive.
Oh, I'm good, I'm sorry. I'm good now.
Okay?
Yes.
Okay, we're almost done with class, so I'm going to just walk right through this one. This is one that I actually intended for you to do, but follow along in this one. We have this slide and then one more slide, and we'll wrap it up, okay? So we want to see where does this expression equal negative 1? I mean, equals, when does this expression, when is it less than 0? So we'll make up our tables. We have 3 intervals, so we're going to, or we have 3 roots, so we're going to have 4 intervals. The 3 that we're interested in are x plus 3, x minus 1, and x minus 2, and we're going to see if that equals, or if that is less than 0. So x plus 3 is negative when we're going from negative infinity to negative 3, but it's going to be positive outside of that. X minus 1 is going to be negative all the way up to when x equals 1, and then from 1 to infinity it's going to be positive. So the first 2 are negative, the second 2 are positive. And then the third one, the x minus 2, is always going to be negative until we are greater than 2, and then it's going to be positive. So if we count up the negative signs we have a negative, positive, a negative, a positive. So what we're looking for here are negative values because we want the expression to be less than 0. And so the first and the third intervals are the ones that are true. And so we're going to have our solution set is going to be those 2 intervals, the union of those 2 intervals. So if we put this on a number line, it's going to look like this. So it's going to be those 2 intervals. Now let's say we were to look at the function, not the inequality, but the function where f at x equals those 3 terms. If I make a graph, this is what it's going to look like, where when x equals 0, you pop in a 0 and you get a 6, and it's going to go from negative to positive and then negative to positive. You see where our solution set is asking us, where does this expression, where is it negative? Well, we can tell by the graph of the function as well. And so these things are very related in terms of, you know, is it going to be on above the x-axis or below the x-axis? This particular equation, of course, is not an equation in 2 variables. It's not a function. It's just a single one in x, so that's why we put it on the number line. Now, the one application of this thing, and then we'll wrap it up here, is that you can find the domain of radical expressions. Like this one, you say, what's the domain of it? Well, the domain is where, let's factor this just to get a little bit better understanding of what the function is. The domain is where the product of those 2 terms is greater than 0. All right? Greater than or equal to 0. That defines our domain for a root function. And so we'll go through that same process, making 3 intervals because we have 2 possible solutions. See where it's positive, see where it's negative. And so it's greater than 0 in the first and the last cases, so our domain then is the union of the two cases where it's where it is positive. Okay, so that's what I got. Look for some homework, and I'll see you on Wednesday.